So, how do we calculate delta G when we're not at standard conditions? When you run reactions, you are not always using 1 molar solutions, or if you're involving gases, you're not always at 1 atmosphere pressure. So what do we do when we're not at standard conditions in order to get accurate values for our thermodynamic quantities? Well, for delta G, we're going to use this equation. Delta G is equal to delta G naught plus RT natural log of Q. All right, what are all these symbols? Q is our reaction quotient, right? It's the same form as the equilibrium constant, but we can use it at any time. It doesn't have to be at equilibrium. R is the universal gas law constant. I more often call this the ideal gas law constant. You're used to seeing the value 0.0821 liter atmospheres per mole Kelvin. Believe it or not, the product of liters and atmospheres is a unit of energy. You may have heard of PV work, pressure times volume work. So we end up with these units of energy. If you convert liter atmospheres to joules, you get 8.314 joules per mole Kelvin. And then let's see what else. The temperature's got to be in Kelvin. Every time we do stuff with thermodynamics, temperature's got to be in Kelvin. And then delta G naught refers to the standard Gibbs free energy change. So check out this equation. We are saying that delta G without the naught, right? So delta G at non-standard conditions, is equal to our standard delta G naught, plus a fudge factor. This fudge factor is RT natural log of Q. So it changes depending on exactly what our conditions are. All right, so we're going to work an example where we use the equation we looked at on the last slide. It says calculate the free energy change delta G of a reaction mixture containing 1.75 atmospheres of NO2 and a half atmosphere of N2O4 at 25 degrees C. This is for the dimerization of NO2 to make N2O4. Notice down the lower left, we are given the delta G is a formation. Oops, there should be an F on that. We are given the delta G's formation of NO2 and N2O4. Couple things to point out here. We're asked to find the free energy change, delta G. Notice there's no naught on this. This one is not a typo. This one is at non-standard conditions because we do not have 1 atmosphere of NO2 and we do not have 1 atmosphere of N2O4. We have different values. So we need to see, we need to use the special equation to calculate that. And that's the equation that says delta G is equal to delta G naught plus RT times the natural log of Q. So I want to do some pre-calculation before we plug numbers into this overall equation. I want to find delta G naught based on the data in the table at the bottom, and I want to find Q. Once we have those two numbers, then we can substitute into this equation. So delta G naught for this equation would be equal to products minus reactants. We have 1 N2O4, and N2O4's value for delta G of formation is 98 kilojoules per mole. And then for the reactants, we have 2 moles of NO2, and NO2 has a value of 52. All right, so we will have 98 minus 2 times 52, which gives us a value of -6. So we have -6 kilojoules for delta G naught. For calculating Q, Q is going to be products over reactants. So that's going to be N2O4 divided by NO2, and NO2 has a coefficient of 2, so it's squared. N2O4 has a pressure of 0.5 atmospheres, and NO2 has a pressure of 1.750 atmospheres, and we're going to square that. So 0.5 divided by 1.75 squared gives us a value of 0.163 for Q. So now that we have Q and delta G naught, we can plug into our equation for delta G. So delta G will be equal to delta G naught plus RT times the natural log of Q. And let's see, delta G naught was -6 kilojoules. And then let's see, R was 8.314 joules per mole Kelvin. That's going to be a problem, right? R is 8.314 joules per Kelvin. And the problem that we're running into is that delta G is in kilojoules. So I need to move that decimal 3 times, which means I'll have to put 2 zeros out in front of it. So that'll be 0.008314 joules per Kelvin. And then our temperature is still 25 degrees C, which is 298 Kelvin. And then we want the natural log of Q, and Q was 0.163. Okay. Let's see if we can run this whole big string through my calculator. Right now I've got the 0.163 still showing, so I'm going to take the natural log of that, which gives me a -1.81. I'm going to multiply that times 298 and times 0.008314. So for that second term, I have a -4.49. And then I need to add to that a -6. And so that's going to end up being, let's go for like 3 sig figs. That'll be a -10.5 kilojoules. And whoops, I just realized this was not joules here, that was kilojoules. All right, so there we go. We've got that delta G for this reaction at non-standard conditions is -10.5 kilojoules. So our objectives were to relate equilibrium to thermodynamics, and we saw how to calculate delta G at non-standard conditions.